Okay, we're going to start by looking at a function that generally doesn't have necessarily a rule for it. We've never probably seen a function like this. I've pretty much just made it up and made some interesting features to it. One of the things that we always do in calculus, and hopefully you've done this in some previous classes, is try to study math from different standpoints. In calculus, we do that a lot. We try to look at things from a graphical standpoint. We try to look at something from a numerical standpoint. And we also do it from an algebraic standpoint. So if we take this particular function, obviously we have a graph for it, so this would be looking at it from a graphical standpoint. If we were to be able to write an equation for this function, okay, that would be algebraic. And there's a lot of things we've done in algebra with equations. We've solved equations. That's kind of the main thing that we've done with them. But bottom line is we can look at it in terms of some kind of algebraic rule. Okay, or we could also look at this as a table of values. If we just were given some table of values, okay, it would obviously not look like a graph. It would just look like a table of values, but then of course we could take that and we could plot it and we could make a graph from it. Okay, so what we're going to start this class with is what we call limits. Okay, and so looking at the function that we were given, okay, what we're going to be asking ourselves is some various questions about the limit of this function at different points. Okay. At this time, that probably doesn't mean a whole lot to us, but when we get done today, hopefully it certainly will. Okay. Now, the first question that I'm going to pose is about the end behavior of this function. Okay, and I stress that it's end behavior because in the past I've said end behavior, and then people write out a test the letter N and then behavior. So it's actually the word end. Okay, so when we deal with end behavior for certain functions, okay, what we're asking for here is what happens to the function as we go off to infinity, either to the left or to the right. So let's start with infinity going to the right. Okay, and again, we don't see all of the function, obviously. We only see the part that's near the origin. But as we see by the arrow, and when we're given any arrow situation, we want to trust what the arrow shows us and the fact that this would, essentially continue to get bigger along that same path for infinity. Okay, so when we look at the left end behavior going on the left side, okay, this particular branch looks like it's getting closer and closer to the y or the x-axis, which it would make that an asymptote for it. Okay, and we know that it's going to get infinitely close to that axis without touching it. Okay, but ultimately its end behavior, okay, is the question that we're going to be asking is what are the y values like when we go off to infinity or negative infinity? Okay, so let's go back to the right one again. If we say that this is going to follow the same path and keep going up, then we would say that as we approach infinity, okay, in other words, as x gets infinitely big, what happens with the y values? The y values also get what? They get big as well. Okay, and we're going to put that into the language of limits here in just a minute. Whereas on this side, as we approach negative infinity, in other words, as x gets infinitely small, what happens to y? Y gets closer and closer to what? To 0. Now, we've all accepted that in Algebra 2 and Pre-Calc, the fact that that doesn't actually ever touch the x-axis. True? It's infinitely close, but it doesn't touch the x-axis. So you told me a minute ago that that it's going to get closer and closer to 0. Okay, and what we do with calculus, the language of calculus will tell us that the limit, okay, as we approach negative infinity, is 0. Okay, so even though we don't actually get to 0, okay, we would write that as the limit as x approaches negative infinity, okay, of this function is 0. So luckily for us, like most math, we have symbols for all that instead of writing out those words. Otherwise, we're going to have to write a paragraph every time we do this. Okay, what it boils down to is in the language of limits, this is what the notation looks like. So let's go through each part of these two notations. Okay, the first one, when we don't even write the word limit, we just write lim. Okay, and then down below, we're going to write this x with an arrow to negative infinity. And the way this is read in English is the limit of f of x as x approaches negative infinity. Okay, so those are the words that go along with the symbols. So if you were to read that to somebody, that's how you'd say it. The limit of f of x. The limit of f of x as x approaches negative infinity equals 0. Okay, so again, graphical, we can see that the curve approaches the x-axis as we go to the left. Okay, in an algebraic sense, this is the symbol for that. Okay, this shows us what's happening. So if I were to give you this and say, well, what's going on? Could you draw me a picture of that? Okay, you would need to associate this situation with this right here. One question was, does it have to be coming from above and approaching 0? Could it be coming from below and approaching 0 also? Yeah, it doesn't really matter whether it's coming from above or below. Bottom line is, as x gets infinitely small, okay, which is this symbol, okay, f of x, which are the y values of the function, get close to 0. Fair enough? And you notice that we put equals 0 here. The limit equals 0. Does the function actually equal 0 ever? No. Okay, but the limit equals 0. So that's important. And what's important to note is that we can say that the limit equals 0 even though the function doesn't ever actually get to that point. Fair enough? Okay. All right, similarly, when we do our whoops, that marked wrong. When we do our limit as f of x approaches positive infinity, and we look at our branch going off in this direction, we already said that this continues to grow. And again, if it continues to grow, it's going to grow without bound. Ultimately, it's going to grow to infinity. All right. Had I turned it back around and went down this way, okay, then we would have had a negative infinity here. True? Okay. All right. Questions so far on the end behavior part? Okay. So just to double check, if we were to ask for what would be this limit? What if I asked you to do what's the limit as x approaches infinity for x squared? Okay. X squared function looks like what? It's a parabola. So if it's a parabola, and again, this indicates that we're going infinitely far to the right. Okay, what are the y values like for a parabola infinitely far to the right? They're infinitely what? They're infinitely big. So the answer here would be again what? Infinity. What if I had changed this to negative infinity down here? Going off to the right, the answer still would have been what? Still would have been infinity, wouldn't it? Okay. So again, this is just a nice way of using limits to describe the end behavior of a function. Okay. It could be negative infinity or infinity, or they could go to some particular asymptote like this one and have an answer like 0. Okay. All right, now let's look at some of these other points that we have here. And we're going to talk about limits from a similar but a little bit different standpoint. Okay. So what we're going to do is we're going to start with the asymptote here. We have an asymptote here at -5. So the question is, how would we describe the behavior around x equals -5 with limits? Okay. So I want you to first look at the notation I have here. I have the limit as x approaches -5, and then there's another little negative sign right here. Okay. And that's not there by accident because, as you can see in the other one, there's a little plus right here. True? All right, and so what it boils down to is this reads almost the same way. We're asking for what's the limit of f of x. Okay. In other words, what are the y values of f of x approaching, or like, when x is approaching -5, and the minus sign means from the left. So if it's -5 minus, that means from the left. All right, and you can see that I have an answer of infinity here, but the question is why? Okay, why is that the answer? Well, let's find -5. It's right here. Okay. As I approach from the left, that means I'm over to the left of the asymptote. Okay, what's going on with my y values as I get closer and closer to -5? The y values are getting what? They're getting higher. They're getting bigger, aren't they? So, again, how big do they get as we approach -5? They get infinitely big, don't they? Okay. So does it make sense that this answer is infinity here? And equally, if I go -5 and the plus sign means from the right, okay, and I start over here on the right side of the function, as close as I can get to -5 is this little branch right here. Okay, what's going on with my y values as I get close to -5 from this side? They're getting smaller, and so therefore the answer here is negative infinity. So when we describe, just to make kind of a generalization, hold on.